December 5, 1944, the Philippine Sea. The destroyer USS Orlik cuts through dark water, her hull trembling with the vibration of her engines. Her crew at battle stations as the sun begins its descent toward the western horizon. The air tastes of salt and fuel oil. The ship's 5-inch guns track restlessly across the sky, searching for threats that could materialize from any direction at any moment. In the Combat Information Center deep within the ship's hull, radar operators watch glowing screens that paint the world in phosphorescent green, translating invisible radio waves into geometry and distance. The war in the Pacific has entered its final terrible phase, and the Japanese have embraced a new doctrine that turns men into weapons, aircraft into manned missiles, suicide into strategy. At 17:42 hours, the radar picks up a contact. Bearing 350, range 20,000 yards and closing fast. The alarm sounds throughout the ship, a Japanese aircraft, probably a Zero or a Naval dive bomber, heading directly toward the formation. Standard procedure would be to alert the combat air patrol, to maneuver for optimal firing position, to prepare for the possibility that this pilot has no intention of pulling out of his dive. But aboard the Orlik and dozens of other American warships in the Pacific Fleet, there is a secret that changes the mathematics of aerial combat so fundamentally that even the officers who use it sometimes struggle to believe the results. The 5-inch guns train toward the approaching contact. The fire control computer calculates trajectory, windage, target speed and altitude, and load it into the guns waiting to be fired. Are shells that carry within their nose cones a technology so revolutionary, so impossible by the standards of conventional munitions, that it represents nothing less than a transformation in the science of war. The shells are proximity fused, and they are about to demonstrate why American ships can create a zone of destruction in the sky that no attacking aircraft can penetrate and survive. The guns fire. The sound is enormous, a percussion that travels through the deck plates and into the bones of every man aboard. The shells arc upward into the darkening sky, their trajectories calculated to intersect with the path of the incoming aircraft. There is no need to score a direct hit, no need for the nearly impossible task of placing a 5-inch shell directly onto a target moving at 300 miles per hour in 3 dimensions. The proximity fuse will detonate the shell when it passes within lethal range of the aircraft, converting each round into an expanding sphere of shrapnel that makes evasion nearly impossible. At 18,000 yards, the first shell explodes in a brilliant flash just 30 feet from the Japanese aircraft. The blast tears through the Zero's wing, shredding control surfaces and fuel tanks. The aircraft begins to tumble, trailing flame and smoke. 2 more shells detonate in rapid succession, and the wreckage impacts the ocean more than 5 miles from the Orlik, never having come close enough to threaten the ship. The entire engagement lasts 43 seconds from first radar contact to final impact. The crew barely has time to register what has happened before they return to scanning the sky for the next threat. This scene repeated itself thousands of times across the Pacific and European theaters in the final years of the war, but its significance extends far beyond any individual engagement. The proximity fuse, officially designated the VT fuse for variable time, represented one of the most closely guarded Allied secrets of World War II, a technological achievement that fundamentally altered the balance of power in the war against both Germany and Japan. And despite years of exposure to the weapon, despite recovering thousands of unexploded shells, despite dedicating their finest scientific minds to the problem, neither the Germans nor the Japanese ever succeeded in duplicating it. To understand why the proximity fuse was so devastating and why the Axis powers could never crack it, we must step back from the Philippine Sea in 1944 and examine the problem that the fuse was designed to solve: anti-aircraft. Gunnery in the early years of World War II was an art of frustration and probability. Hitting a fast-moving aircraft with an explosive shell required solving an extraordinarily complex three-dimensional calculus in real time. The target was not merely moving, but maneuvering, changing altitude and course in response to the gunfire itself. The shell had to be fired not at where the aircraft was, but at where it would be when the shell arrived at altitude, a calculation that involved predicting the target's future position while accounting for wind, air pressure, temperature, the decreasing velocity of the shell as it climbed, and a dozen other variables, even with sophisticated fire control. Computers themselves a cutting-edge technology in the early 1940s. Actually, hitting an aircraft with a timed fuse shell was extraordinarily difficult. Traditional anti-aircraft ammunition used a mechanical time fuse that was set before firing to detonate at a specific altitude. If the calculations were perfect and the aircraft maintained its course and speed, the shell might explode near enough to damage or destroy the target. But if any variable was incorrect, if the aircraft altered course, if the fuse timing was off by even a fraction of a second, the shell would explode harmlessly in empty sky. The statistics were grim. In 1942, American and British anti-aircraft batteries expended an average of more than 2,500 rounds per aircraft destroyed. German flak batteries had similar hit rates against Allied bombers. The sky could be filled with exploding shells, but the odds of any individual round achieving a kill were vanishingly small. For ships at sea, the problem was even more acute. Naval anti-aircraft batteries had to contend with the movement of their own platform, as well as the target's maneuvers, and the window of effective engagement was measured in seconds as fast-moving attackers closed to torpedo or bombing range. The advent of the kamikaze in late 1944 made this problem existential. A conventional attacking aircraft might be driven off by anti-aircraft fire, even if not destroyed outright. A pilot who saw shells bursting around his aircraft might break off his attack run to evade. But a kamikaze pilot was committed to the attack regardless of damage, and would continue toward his target until either destroyed completely or until he struck home. Against such an enemy, near misses meant nothing. Only immediate destruction of the incoming aircraft could prevent damage to the ship. The proximity fuse solved this problem with an elegance that bordered on the miraculous. Instead of requiring a direct hit or perfect timing, the fuse used a miniature radio transmitter and receiver built into the shell's nose cone. As the shell flew through the air, the transmitter emitted a continuous radio signal. When the shell passed close to a large metal object, like an aircraft, the radio waves reflected back to the receiver. When the strength of the reflected signal exceeded a predetermined threshold, indicating that the shell was within lethal range, the fuse triggered detonation. The result was a weapon that could miss by 50 feet and still destroy its target. Every proximity-fused shell created a sphere of destruction, roughly 100 feet in diameter. An aircraft that flew anywhere within that sphere faced shrapnel moving at thousands of feet per second, tearing through aluminum skin and aircraft systems. The pilot had no warning, no opportunity to evade. The only way to survive was to stay entirely outside the engagement envelope, but that meant abandoning the attack entirely, but describing the proximity. Fuse's function does not capture the extraordinary technical achievement it represented or explain why the Axis powers, despite possessing sophisticated scientific establishments and desperate need for the technology, could never duplicate it. The development of the proximity fuse began in 1940, when British scientists approached their American counterparts with the problem of improving anti-aircraft effectiveness. Britain was under sustained aerial bombardment, and the limitations of conventional anti-aircraft fire were becoming painfully apparent. The initial concept was straightforward: create a fuse that could detect proximity to a target and detonate automatically. But the engineering challenges were staggering. The fuse had to survive being fired from a gun, an acceleration of 20,000 times the force of gravity. that lasted for milliseconds, but was sufficient to destroy almost any electronic device. It had to remain functional after being subjected to centrifugal forces as the shell spun at hundreds of revolutions per second to maintain stability in flight. It had to operate reliably in temperatures ranging from Arctic cold to tropical heat, in rain and humidity, after sitting in storage for months or years. It had to be mass-produced by the millions, at a cost low enough to be economically feasible. Individual shells could not cost more than the aircraft they were designed to destroy. And perhaps most challenging of all, the radio transmitter, receiver and detonation circuit had to be miniaturized to fit inside a shell nose cone only a few inches in diameter. Built using vacuum tube technology that in 1940 typically required equipment the size of a radio console. The problems were so severe that many experienced engineers declared the concept impossible. But the National Defense Research Committee, working with laboratories and manufacturers across the United States, approached the problem with a combination of innovative design and brute force engineering that would become characteristic of American wartime technology development. The solution required inventing entirely new manufacturing processes. Standard vacuum tubes were too large and too fragile, so engineers developed miniature tubes specifically for the proximity fuse, with filaments and components designed to withstand the shock of firing. The radio circuit was simplified to its absolute essentials, using a design that sacrificed range and precision for ruggedness and reliability. The battery that powered the circuit was activated by the centrifugal force of the shell's spin, ensuring that the fuse could not detonate prematurely during storage or handling. Every component was tested and retested, subjected to accelerations that destroyed prototype after prototype, until finally, incrementally, a design emerged that could survive the violence of being fired and still function reliably. The first successful test of a proximity-fused shell occurred in August 1942, when a 5-inch round fired over Chesapeake Bay successfully detonated near a radio-controlled target drone. But testing was one thing. Mass production was another. The proximity fuse required precision manufacturing at a scale unprecedented in military ordnance. Vacuum tubes had to be assembled by hand by workers trained to tolerances measured in thousandths of an inch. Radio circuits had to be calibrated and tested individually. Quality control was paramount. A single defective fuse could fail to protect a ship or aircraft, with potentially fatal consequences. American industry rose to the challenge with characteristic intensity. At peak production, American factories manufactured more than 70,000 proximity fuses per day. The total wartime production exceeded 22 million fuses, each one containing technology that represented the cutting edge of radio and electronics engineering. The cost per unit dropped from more than $700 for early prototypes to less than $20 for mass-produced versions, cheap enough that proximity-fused ammunition could be expended freely without concerns about cost. The results were extraordinary. In the Pacific Theater, ships equipped with proximity-fused ammunition shot down aircraft at more than 3 times the rate of ships using conventional timed fuses. In the European theater, proximity-fused anti-aircraft shells proved devastatingly effective against German V-1 flying bombs, destroying more than 80% of the V-1s engaged. When proximity-fused shells were adapted for ground bombardment use during the Battle of the Bulge in December 1944, they proved equally lethal against infantry and vehicles. The airbursts eliminated the need for direct hits and made conventional entrenchments far less effective as protection. But perhaps the most remarkable aspect of the proximity fuse was not its effectiveness, but the fact that the Axis powers never succeeded in duplicating it, despite having every motivation to do so and despite recovering thousands of examples. German forces began recovering unexploded proximity-fused shells as early as 1943, when American forces deployed the weapons against V-1 attacks over Britain. Duds fell into German hands during the Battle of the Bulge. Japanese forces recovered proximity-fused shells from naval engagements in the Pacific. In each case, Axis scientists and engineers had access to intact examples of the technology they were trying to duplicate. They could disassemble the fuses, examine the components, trace the circuits, and understand the basic operating principle. Yet despite this access, despite years of effort, despite the desperate need for improved anti-aircraft capabilities as Allied bombing intensified, neither Germany nor Japan ever fielded an operational proximity fuse. The reasons for this failure reveal fundamental differences in the industrial and scientific capabilities of the Allied and Axis powers, differences that extended far beyond any single technology and help explain the ultimate outcome of the war itself. The proximity fuse was not merely a clever device that could be copied by anyone with access to an example. It was the product of an integrated system of scientific research, precision manufacturing, quality control, and mass production that the Axis powers could not replicate, even when they understood what needed to be done. German scientists who examined captured proximity fuses recognized their importance immediately. Reports sent to Berlin described the devices in detail and recommended urgent efforts to develop German equivalents. The German electronics industry was sophisticated and capable. German radio and radar technology was in many respects equal or superior to Allied equivalents. But the proximity fuse required more than sophisticated design. It required the ability to manufacture millions of precision electronic devices in a form factor small enough to fit inside an artillery shell and rugged enough to survive being fired from a gun. This was precisely the kind of mass production of precision technology at which American industry excelled and German industry struggled. The German war economy, despite its reputation for efficiency, was actually characterized by small batch production of highly complex weapons, often using skilled craftsmen to hand-build components. This approach could produce excellent individual examples. German tanks, aircraft, and weapons were often superior in design to their Allied counterparts, but it could not match the scale of American mass production. Where American factories might produce thousands of identical components using automated machinery and unskilled labor, German factories produced hundreds using skilled workers and hand-fitting. The proximity fuse exposed this limitation mercilessly. German engineers who attempted to duplicate the technology found themselves unable to manufacture the miniature vacuum tubes in sufficient quantity and quality. The tubes that worked in prototypes failed in testing when subjected to the shock of firing. Attempts to simplify the design reduced reliability below acceptable levels. Quality control systems could not maintain the necessary tolerances when production scaled beyond prototype quantities. By the time German engineers had solved one problem, they encountered another, and the pace of problem-solving could not keep up with the pace of Allied bombing and the deterioration of German industrial capacity. The German military leadership, recognizing that a German proximity fuse would not be available in time to affect the war, attempted to develop countermeasures instead. One approach was to cover German aircraft with radar-absorbing materials that might reduce the reflected signal and prevent the fuse from detonating. This proved impractical. The materials added weight and cost without providing reliable protection. Another approach was to use electronic jamming to interfere with the fuse's radio signal. But the fuses operated on frequencies that were difficult to jam effectively, and widespread jamming would have interfered with German radar and communication systems. In the end, German forces had no effective counter to proximity-fused shells except to avoid areas where they were deployed, which meant avoiding Allied ships and ground positions, which meant conceding control of the battlefield and the sea. The proximity fuse became one more advantage that Allied forces could leverage, one more way in which superior technology and industrial capacity translated into tactical and strategic dominance. The Japanese experience with the proximity fuse followed a similar pattern, but with even more desperate consequences given Japan's increasingly precarious military situation in 1944 and 1945. Japanese forces first encountered proximity-fused shells during naval engagements in late 1943, and the impact was immediately apparent. Japanese pilots who had grown accustomed to the predictable patterns of timed anti-aircraft fire found themselves flying through an aerial killing zone where shells seemed to know exactly where to explode. Attack runs that should have succeeded ended with aircraft disintegrating in mid-air before they could release their weapons. The kamikaze tactics that Japan adopted in desperation as its pilot training programs collapsed and conventional attacks became unsustainable, were far less effective against ships equipped with proximity-fused ammunition. Japanese naval intelligence recognized the proximity fuse as a critical technology and assigned high priority to understanding and duplicating it. Recovered shells were sent to laboratories in Japan for analysis. Engineers successfully disassembled the fuses and identified the key components. Reports to Naval General Staff described the device's operation in accurate detail. But as with the Germans, understanding the technology and reproducing it proved to be entirely different challenges. Japan's electronics industry in 1944 was sophisticated. In some respects, Japanese radar technology had advanced considerably during the war, and Japanese radios and communications equipment were generally adequate, if not equal, to Allied standards. But the miniaturization and ruggedization required for the proximity fuse exceeded Japanese manufacturing capabilities. Japanese industry had always emphasized quality and craftsmanship over quantity and mass production. In peacetime, this approach had produced excellent results. In wartime, facing an enemy with overwhelming industrial capacity, it became a fatal limitation. Japanese engineers who attempted to duplicate the proximity fuse faced the same problems that plagued their German counterparts, but with fewer resources and less time. The miniature vacuum tubes could not be manufactured reliably in quantity. The assembly process required precision that Japanese factories, increasingly battered by American bombing and starved of raw materials, could not maintain. Prototypes worked in laboratory conditions, but failed when subjected to the shock and spin of actual firing. And unlike Germany, which at least maintained industrial capacity until mid-1944, Japan's manufacturing base was actively deteriorating throughout the period when engineers were trying to solve these problems. The strategic impact was profound. American naval forces, equipped with proximity-fused ammunition and increasingly sophisticated radar fire control systems, created defensive zones around their ships that Japanese aircraft could not penetrate with acceptable losses. The kamikaze strategy, which Japanese military leadership had adopted as a force multiplier that could compensate for the loss of experienced pilots, proved far less effective than anticipated. While individual kamikaze attacks sometimes succeeded, particularly when Japanese aircraft attacked in large coordinated groups that could overwhelm defenses, the overall exchange ratio heavily favored the Americans. Statistical analysis of kamikaze attacks reveals the proximity fuse's impact with brutal clarity. In engagements where American ships used conventional, timed fuse anti-aircraft ammunition, approximately 20% of kamikaze aircraft succeeded in striking their targets. In engagements where proximity-fused ammunition was available, the success rate dropped to less than 7%. For the Japanese Navy, which had committed itself to the kamikaze strategy because it lacked alternatives, this difference was catastrophic. The tactic was already unsustainable in terms of pilot losses. It required a constant stream of barely trained pilots who would fly one mission and never return. But when the success rate of those missions dropped by 2/3, the entire strategic calculation collapsed. The symbolic significance of the proximity fuse extended beyond its immediate tactical effects to represent something fundamental about American power and the Allied advantage in industrial and scientific capacity. The fuse was, in its physical form, a small object, a metal cylinder a few inches long, weighing less than a pound, containing circuits and components that would have seemed impossibly delicate to anyone who had not witnessed their creation. But that small object embodied vast systems that stretched across the American continent and reached deep into the industrial and scientific infrastructure that the United States had built over decades of peacetime development. The miniature vacuum tubes came from factories that had refined their manufacturing processes through years of commercial radio production. The precision machining came from machine shops that had learned their craft-building automobiles and appliances. The quality control systems came from American management sciences that emphasized standardization and statistical process control every proximity fuse carried. With it, the imprint of the system that had created it. When a shell detonated near a Japanese aircraft over the Philippine Sea, destroying the plane and killing its pilot, the explosion represented not just American technology, but American industrial organization, American scientific infrastructure, American manufacturing capacity, and American ability to innovate and mass-produce simultaneously. The pilot never saw the shell that killed him, never knew about the radio waves that detected his aircraft's approach, never understood that he had been destroyed by a technology his own nation's scientists understood but could not reproduce. This theme, American abundance and industrial capacity made manifest in small objects deployed by the millions, recurs. Throughout the Pacific War, the proximity fuse joined the Jeep, the Liberty ship, the C-47 transport, the M1 Garand rifle, and 100 other pieces of equipment that were individually unremarkable but collectively overwhelming. Where Japanese soldiers fought with equipment that was often excellent in design but always scarce in supply, American forces had sufficiency in everything. Where Japanese aircraft attacked in desperate attempts to slow the American advance, knowing that neither they nor their pilots could be replaced, American ships defended themselves with ammunition that cost millions of dollars per engagement but was available in unlimited quantity. The psychological impact of this disparity was as significant as the material effect. Japanese pilots who survived encounters with proximity-fused anti-aircraft fire reported that the experience was fundamentally different from conventional flak. Traditional anti-aircraft fire, no matter how intense, created patterns that skilled pilots could learn to evade. The shells exploded at predictable altitudes, creating clouds of shrapnel that could be avoided through the right combination of speed, altitude changes, and jinking maneuvers. But proximity-fused shells created no such patterns. They exploded wherever the aircraft happened to be, following the pilot through evasive maneuvers, detonating at the moment of closest approach regardless of altitude or course. The effect was uncanny, almost supernatural, as if the shells themselves were intelligent and hunting the aircraft deliberately. This sense of facing an enemy with impossible capabilities, with technology that bordered on magic, contributed to the psychological collapse that affected Japanese military morale in the final year of the war. Japanese soldiers and sailors had been taught that Japanese spirit could overcome American materialism, that dedication and sacrifice could defeat industrial production, that individual excellence could triumph over mass-produced adequacy. The proximity fuse, along with the radar systems that detected aircraft before they appeared on the horizon, and the communications networks that coordinated defensive fire across entire fleets, demonstrated that this ideology was fantasy. American forces were not weak despite their abundance. They were strong because of it. Their system produced not just more weapons, but better weapons, and it did so in quantities that made numerical comparisons meaningless. The development and deployment of the proximity fuse also revealed critical differences in how the Allied and Axis powers approached military technology and scientific research during the war. The United States entered World War II with a deliberate strategy of mobilizing its scientific community for military purposes. The National Defense Research Committee, later reorganized as the Office of Scientific Research and Development under Vannevar Bush, created a system that linked academic researchers, industrial laboratories, and military requirements in an integrated network. Scientists from universities across the country worked on military problems while maintaining their academic affiliations. Industrial laboratories contributed their expertise in manufacturing and production engineering. Military officers provided practical knowledge of battlefield requirements. The result was a collaborative system that could move from basic research to mass production with unprecedented speed. The proximity fuse exemplified this approach. The initial concept came from British researchers. American scientists at the Carnegie Institution, the National Bureau of Standards, and Johns Hopkins University's Applied Physics Laboratory developed the theoretical design and created working prototypes. Industrial partners including Eastman Kodak, Crossley Corporation, and Sylvania Electric Products developed the manufacturing processes and quality control systems that enabled mass production. Military officers from the Navy Bureau of Ordnance and Army Ordnance Department provided feedback from field testing and combat use, leading to continuous refinement and improvement. This collaborative model allowed rapid iteration and problem-solving at scale. When early proximity fuses proved susceptible to premature detonation in heavy rain, researchers identified the problem, developed a solution, and had modified fuses in production within months. When combat experience revealed that the fuse's detection range could be optimized for different targets, engineers created multiple variants tuned for anti-aircraft use, ground bombardment, and naval fire. The system was flexible, responsive, and capable of managing enormous complexity while maintaining momentum toward deployment. Germany and Japan, by contrast, approached military technology development in ways that emphasized secrecy, compartmentalization, and separation between military and civilian spheres. German weapons development was divided among competing bureaucracies: the Army Ordnance Office, the Luftwaffe's Technical Services, the Navy's Weapons Development Branch, and various SS organizations that often worked at cross purposes and refused to share information. Promising technologies might be pursued by multiple groups simultaneously without coordination, or abandoned entirely if they fell outside bureaucratic boundaries. Scientists and engineers often lacked direct access to battlefield feedback, developing weapons based on theoretical requirements rather than practical combat experience. Japan's system suffered from similar fragmentation, exacerbated by the rivalry between the Army and Navy that led to separate and often incompatible weapons development programs. Japanese military culture also emphasized secrecy to a degree that hindered effective research collaboration. Scientists working on sensitive projects were often forbidden from discussing their work with colleagues who might have provided crucial insights. Information about Allied weapons and capabilities, gathered through intelligence collection and examination of captured equipment, was often restricted to small groups rather than disseminated widely to researchers who could have acted on it. These organizational differences help explain why the Axis powers could not duplicate the proximity fuse despite having access to examples and understanding the underlying principles. Duplicating the technology required not just scientific knowledge, but industrial capability, manufacturing expertise, quality control systems, and organizational structures that could coordinate across institutional boundaries and move from understanding to production rapidly. The Allied powers, particularly the United States, had built such systems over decades of peacetime development. The Axis powers had not and could not create them in the middle of a losing war, while under sustained bombardment and facing resource shortages. By early 1945, the proximity fuse had become so thoroughly integrated into American anti-aircraft defenses that its presence was assumed in operational planning and tactical doctrine. Naval vessels operating in the Pacific carried proximity-fused ammunition as standard, with conventional timed fuse shells relegated to secondary status or shore bombardment use, where the fuse's sensitivity to ground returns made it unsuitable. Anti-aircraft batteries defending London against V1 attacks used proximity-fused shells almost exclusively, achieving destruction rates that rendered the V1 campaign nearly ineffective, despite the German launch of more than 10,000 flying bombs. American artillery batteries in Europe loaded proximity-fused shells for use against German infantry and armor, particularly in situations where German forces were attacking across open ground and airbursts would be most effective. The widespread deployment raised security concerns that had been present from the beginning of the proximity fuse program. Allied commanders recognized that the fuse represented a technological secret of extraordinary value, comparable to radar or cryptographic breakthroughs like the breaking of the Enigma code. If the Axis powers obtained intact examples and successfully duplicated the technology, the Allied advantage would evaporate. Worse, proximity fuse shells used by German anti-aircraft batteries against Allied bombers could dramatically increase Allied casualties and potentially threaten the strategic bombing campaign that was systematically destroying German industrial capacity. These concerns led to strict controls on proximity fuse deployment. For the first year after the technology became available, use was restricted to naval anti-aircraft fire over water, where any unexploded shells would sink and be unrecoverable. Use over land was prohibited, except in specific circumstances, where the risk of recovery by enemy forces could be minimized. Even after these restrictions were relaxed in late 1944, commanders were instructed to account for expended proximity-fused ammunition and to recover duds whenever possible. Despite these precautions, Axis forces did recover intact or partially intact proximity fuses, particularly after the Battle of the Bulge, when large numbers of proximity-fused artillery shells were fired over ground held by German forces. But by late 1944, the security considerations had shifted. Allied intelligence assessments concluded that even if Germany or Japan obtained complete documentation and intact examples of the proximity fuse, they lacked the industrial capacity to produce operational versions in militarily significant quantities before the war ended. The Axis powers were losing, not because they lacked knowledge, but because they lacked the industrial and organizational capability to act on that knowledge effectively. This calculation proved correct. German engineers who examined captured proximity fuses in late 1944 and early 1945 confirmed what their earlier assessments had concluded. The technology could be understood, but not duplicated, given Germany's deteriorating industrial situation. Factories that might have produced the miniature vacuum tubes were being destroyed by Allied bombing. The skilled workers who could have assembled the delicate components were being drafted into combat units to replace mounting casualties. The quality control systems necessary to ensure reliable function were breaking down as the German war economy collapsed under the combined pressure of material shortages, transportation disruption, and administrative chaos. Japan's situation was even more dire. By early 1945, American submarines had effectively severed Japan's maritime supply lines, cutting the home islands off from resource supplies in the conquered territories. Japanese factories were running out of raw materials, spare parts, and energy. The firebombing campaign that began with the March 1945 attack on Tokyo systematically destroyed Japan's industrial capacity, burning out entire districts that contained the small workshops and factories where precision components might have been manufactured. Even if Japanese engineers had solved all the technical problems associated with proximity fuse production, the industrial base necessary to implement the solution no longer existed. The final months of the war demonstrated the proximity fuse's impact at its most extreme during the battles for Iwo Jima and Okinawa, where American naval forces faced sustained kamikaze attacks and proximity-fused ammunition proved essential to fleet survival. At Okinawa, from April through June 1945, Japanese forces launched more than 1,900 kamikaze sorties against American ships supporting the invasion. The attacks came in waves, with dozens or sometimes hundreds of aircraft attacking simultaneously to overwhelm defensive fire. American ships formed picket lines around the invasion fleet, positioned to detect incoming raids and provide advance warning. These radar picket destroyers bore the brunt of kamikaze attacks, and their survival often depended on the effectiveness of their anti-aircraft fire. The statistics from Okinawa are telling. American ships fired more than 460,000 rounds of 5-inch ammunition during the campaign, with the majority being proximity fused. They shot down more than 1,500 attacking aircraft, a destruction rate that would have been impossible with conventional ammunition. But even this effectiveness came at a cost. 36 American ships were sunk and 368 damaged, with casualties exceeding 9,000 sailors killed or wounded. The kamikaze attacks that did succeed often came from aircraft that penetrated the defensive zone during coordinated mass attacks, when the volume of fire saturated the defenses despite the proximity fuse's lethality. For the Japanese, the Okinawa campaign represented the culmination and failure of the kamikaze strategy. Japanese military leadership had committed to the tactic as a way to inflict casualties that might force the Americans to negotiate rather than invade the home islands. The plan required sinking or disabling enough American ships to make the cost of invasion unacceptable. But the exchange ratios, even with massed coordinated attacks, favored the Americans decisively. Japan was losing aircraft and pilots at a rate far exceeding American naval losses, and the pilots could not be replaced, while American ships, even when damaged, were often repaired and returned to service within weeks. The proximity fuse was not solely responsible for this outcome. American fighter pilots, sophisticated radar and communication systems, and the ship's own maneuverability all contributed to the defensive success. But the proximity fuse was the weapon system that converted detection and tracking into actual kills, that transformed the knowledge that enemy aircraft were approaching into the destruction of those aircraft before they could strike. Without it, American naval losses at Okinawa might have been double or triple what they actually were, and the kamikaze strategy might have achieved its objective of making invasion too costly to contemplate. The truth that emerged from the proximity fuse's development and deployment cut to the heart of the fundamental asymmetry between Allied and Axis industrial and scientific capacity. The Axis powers entered World War II with technological advantages in some areas: German tanks and aircraft, Japanese torpedoes and fighters, Italian naval architecture, all represented sophisticated engineering and design. But these advantages were narrow, specific, and difficult to maintain or expand in the face of Allied industrial mobilization. The Allied powers, particularly the United States, brought to the war not just superior numbers, but superior systems. Systems for research, for manufacturing, for quality control, for logistics, for training, for continuous improvement and adaptation. The proximity fuse embodied these systemic advantages in a form that could be held in one hand. It represented the American ability to pursue fundamental research while simultaneously developing manufacturing processes. It demonstrated American industrial capacity to mass-produce precision technology at a scale that made cost per unit irrelevant. It showed American organizational capability to coordinate across institutional boundaries and move from concept to deployment in less than 3 years. And it proved that American forces could maintain technological superiority while producing overwhelming quantities, defeating the assumption that quality and quantity were opposing choices rather than complementary. Achievements. German and Japanese engineers who examined captured proximity fuses understood intellectually what they were seeing, but understanding was not enough. They lacked the industrial capacity to manufacture the components, the quality control systems to ensure reliable function, the organizational structures to coordinate development and production, and the resources to pursue the technology while simultaneously fighting a losing war on multiple fronts. The proximity fuse defeated them, not because the principle was incomprehensible, but because the system that had created it was inimitable. This was the deeper meaning of the proximity fuse's 3-to-1 improvement in aircraft destruction rates. The improvement was not merely technical, but systemic. Not merely about one weapon, but about the entire infrastructure of science, industry, organization, and doctrine that enabled that weapon's creation and deployment. When a proximity-fused shell destroyed a Japanese aircraft over the Philippine Sea or a German V-1 over London, it represented the victory of a system of industrial democracy over systems of authoritarian control, of collaborative scientific research over compartmentalized secrecy, of mass production over craft manufacture, of abundance over scarcity. The Axis powers could not crack the proximity fuse because cracking it would have required not just understanding the technology, but transforming their entire approach to weapons, development and industrial production. It would have required abandoning the organizational structures and cultural assumptions that had led them into war in the first place. And that transformation, even if theoretically possible, could not be accomplished in the middle of a war they were already losing, by nations whose industrial bases were being systematically destroyed, with resources and time they did not possess. The war ended with the proximity fuse still a closely guarded secret, though its effects had been observed by every Axis power that had faced it. After Japan's surrender in August 1945, American technical intelligence teams swept through Japanese military installations and research facilities, collecting documents and interviewing scientists and engineers about their weapons development programs. Among the documents recovered were detailed analyses of the proximity fuse, based on examination of captured shells, along with reports describing Japanese attempts to duplicate the technology. The reports were technically accurate and showed that Japanese engineers fully understood what they were trying to achieve. But the manufacturing section of each report ended with the same conclusion. Production is not possible with current industrial capacity. Similar documents recovered from Germany showed an almost identical pattern. German scientists had correctly identified the proximity fuse's operating principle, had designed circuits that would theoretically work, had even produced small numbers of prototype fuses that functioned in laboratory testing. But none of this had translated into operational weapons. The gap between prototype and mass production, between laboratory success and battlefield deployment, proved unbridgeable. In the post-war period, the proximity fuse became one of the technologies that symbolized American scientific and industrial achievement during World War II, alongside radar, the atomic bomb, and antibiotics. Veterans who had served on ships in the Pacific told stories of watching proximity fuse shells detonate precisely around incoming kamikaze aircraft, creating a defensive barrier that had saved their lives and their ships. Artillery crews who had used proximity-fused shells in ground combat described the devastating effectiveness of airbursts against enemy positions. The weapon's effectiveness and the Axis powers inability to duplicate it became part of the narrative of American technological superiority that shaped Cold War perceptions of national capability. But perhaps the proximity fuse's most lasting impact was not on the outcome of World War II, which was already determined by larger factors of industrial capacity and manpower, but on the post-war development of military technology. The lessons learned from the proximity fuse program about miniaturization, about ruggedization of electronics, about systems integration, about the importance of moving rapidly from research to production, influenced American weapons development for decades. The scientists and engineers who had worked on the proximity fuse went on to develop radar-guided missiles, transistorized electronics, satellite systems, and the integrated circuits that would eventually enable the digital revolution. The organizational structures that had coordinated proximity fuse development became models for post-war research organizations like DARPA and the National Laboratory System. The symbolic object that American forces had deployed by the millions against Axis aircraft became a symbol in memory as, well, a representation of the moment when American industrial and scientific capacity transformed from potential into overwhelming reality. When the systems that had been built during decades of peacetime development proved their worth in the most demanding test imaginable, the proximity fuse shot down 3 times more aircraft than conventional ammunition, not because it was 3 times more clever, but because it was the product of a system that was incomparably more capable, more flexible, more innovative, and more powerful than anything the Axis powers could create or counter. The destroyer Orlik survived the war, as did most of her crew, protected by proximity-fused shells that detonated around incoming aircraft with geometric precision, creating zones of destruction that Japanese pilots could not penetrate and survive. The shells themselves, after they exploded, left no trace except the expanding spheres of shrapnel that tore through aircraft aluminum and the falling wreckage that marked where the fuse had functioned as designed. But in the moment of detonation, each shell represented the culmination of a vast pyramid of effort. The scientists who had designed the circuits, the engineers who had developed the manufacturing processes, the factory workers who had assembled the components, the quality control inspectors who had tested each unit, the logistics personnel who had transported the ammunition across the Pacific, the fire control technicians who had maintained the radar systems, the gun crews who had loaded and fired the shells. All of this complexity, all of this organization, all of this industrial and scientific capability, compressed into a cylinder of metal a few inches long, launched into the sky at thousands of feet per second, detonating at precisely the right moment to convert potential energy into expanding shrapnel that defended a ship and killed an enemy pilot who never understood what had destroyed him. This was American power made manifest, industrial democracy's answer to authoritarian militarism, the demonstration that free societies fighting for survival could mobilize resources and capabilities that closed societies could never match. The Axis powers never cracked the proximity fuse because it was never really a code to be cracked. It was the visible expression of systemic advantages that ran deeper than any single technology, advantages rooted in industrial capacity, scientific infrastructure, organizational flexibility, and the ability to collaborate across institutional boundaries. These advantages had been decades in the building and could not be duplicated by nations that had taken a different path, that had chosen authoritarian control over democratic collaboration, that had emphasized ideology over pragmatism, that had built their military power on foundations of conquest and exploitation rather than industrial productivity and scientific research. When the proximity-fused shell detonated 30 feet from the incoming zero on that December evening in the Philippine Sea, creating a sphere of shrapnel that tore through the aircraft and sent it tumbling into the ocean. The explosion illuminated a truth larger than that individual engagement. It showed that the war had never been merely a contest of courage or determination. That spiritual strength and willingness to sacrifice, however genuine, could not overcome the material and organizational advantages that the Allied powers, particularly the United States, had built into every aspect of their military systems. The shell destroyed the aircraft, but it also destroyed the illusion that technological superiority belonged to the Axis powers, that American abundance meant American weakness, that industrial capacity was less important than ideological purity or warrior spirit. The proximity fuse's 3-to-1 advantage in aircraft destruction was not an accident of design or a fortunate discovery. It was the inevitable result when a system capable of producing 22 million precision electronic devices faced systems that could barely produce prototypes. It was what happened when collaborative scientific research confronted compartmentalized secrecy. It was the outcome when industrial democracy mobilized its full capability against authoritarian militarism. The Axis powers never cracked the proximity fuse because cracking it would have required becoming something they were not, building capabilities they did not possess, abandoning assumptions that had led them into war in the first place. And so the shells continued to fire, millions of them, throughout the final year of the war, each one carrying within its nose cone the miniature radio transmitter that made it far more than an ordinary projectile. Each one creating a zone of destruction that protected Allied forces and destroyed Axis aircraft. Each one representing a victory won not on the battlefield alone, but in the laboratories and factories and organizational structures that had made such weapons possible. The proximity fuse shot down 3 times more aircraft because the system that created it was incomparably more capable than the systems that opposed it. That was the truth that the Axis powers learned too late, in the wreckage of their aircraft falling from the sky, destroyed by a technology they understood but could never duplicate, defeated by an advantage they could recognize but never overcome.